Basic Calculus, Part 4, Stationary Points. We're now going to draw some graphs. A lot of it is to do with the gradients of graphs. Notice that positive gradient, naught, negative gradient, naught, positive gradient. And that, of course, is the derivative, the gradient, the rate of change. There's a positive gradient going upwards as we go to the right. And since the derivative is equal to the gradient, the derivative is greater than naught. It's positive. Negative gradient going down to the right. And negative gradient means negative derivative. Now we're going to look at these stationary points as to what they mean. A function has three possibilities: increasing, decreasing, or neither. Which means that these points can be behaving in three different ways. We're going to say it's increasing again, decreasing, and the neither we call stationary, meaning not changing. So if you look, there's a positive gradient, increasing, climbing as we go to the right. At that point, the gradient, it's neither increasing nor decreasing, so the gradient is zero. If you had to draw a tangent there, you have a horizontal line and the gradient of a horizontal line. Change in y is zero between 2 points on a horizontal line, so it's 0 over change of x, which is 0. Decreasing, negative gradient, derivative less than naught, derivative negative. Stationary again. And increasing, positive gradient, derivative greater than 0, derivative positive. And those are what we call the stationary points. Notice local maximum, because this one here is going to go upwards. We can't say this is the highest value of the graph, because what about on this part of the curve, way up there? We can't say that's the lowest part of the graph, because what about going way down here? But it's a local maximum. In that area, he's the chief there. Not the whole wider community. He's the chief there, but not the whole wider community. Then there's also a stationary point, but notice increasing, then stationary, f prime x equals 0, and then increasing again. Or it can be the other way around, and that's called the point of inflection. Let's do a couple of examples. Right, so now to find the stationary point, I must put the derivative equal to 0, because that's what happens at the stationary point. Get x equal to 4. Substitute into the original to get the y value. Don't substitute into the derivative. You'll get 0, because that's how you got the 4, by putting it equal to 0. Negative 15, and there's our stationary point. Differentiate, equal to 0. I can see there's a common factor of 3 throughout, so I can divide right through by 3, only because it's an equation. If it's not an equation, I can take out a 3, but I can't get rid of it. Factorize, two possible x values, substitute both into the original, and we have our two stationary points. Here's an exercise for you to do. Pause, try it first before going on. Derivative equal to 0, solve for x, substitute back in the original, stationary point. Derivative equal to x, 0, solve. Now we could have Use difference of squares, kept 4 on this side. Either way is acceptable, but don't forget if x squared equals 4, x is plus or minus 2. The only time you don't introduce the plus or minus and get rid of the square is if x is representing a distance or a time, some physical measurement. Substitute both of them, and there are stationary points. Now we're going to look at the nature of stationary points. Minimum, decreasing, 0, increasing. Maximum, increasing, stationary, decreasing. Inflection, decreasing, stationary, decreasing, or increasing, stationary, increasing. Notice the value of the derivative corresponds with the gradient always. Negative gradient, negative derivative. Negative gradient, negative derivative. Positive gradient, positive derivative. Positive gradient, positive derivative. And the same with these. Right, let's have a look at these now. So, this is the one we did before. We did that, and we now going to investigate before and after 4, because we know stationary at 4. It's equal to 0, the derivative. So we draw up a table. Before 4, 4, after 4. We know it's 0 there, because we found that. We found 4 from putting it equal to 0. If we substitute 4 back in there, we get 0. Now we test a value less than 4. Now, if I choose 0, it won't encroach on any other area this side because there's no other areas, and 0's the easiest to substitute, and I can see I'm going to get a negative. We don't need the value, we just need the sign. A value greater than 4, let's substitute 5, 6, 10, whatever, and we get a positive. Now negative gradient means the line's going this way. That's stationary, horizontal, and positive upwards. There we are. And that tells us the shape of the graph. That's a local minimum. This is actually an absolute minimum in this case, really, because it's a parabola and it only has one turning point. This is going to have 2 turning points. Derivative equal to 0. We did that. Now we're going to investigate 3 areas. You see, because we have 2 where it's 0. So we're going to draw up the table. We have the 2, and we're going to say before, between, after. We're going to substitute values in. Awful, I've got to substitute something like negative 2. I can see without evaluating totally that it's going to be a positive. If we substitute a very big negative like negative 100, this is going to be a big positive, very big positive number. That's going to be positive, positive overall. Between the 2, well, substitute 0, and I can see I'm going to get a negative. Afterwards, we need to substitute something like 4. We get a positive. So there are the lines, which means there's the shape. Nice wave. Maximum, minimum. Local. Exercise for you to do. Pause. Do them first. Derivative equal to 0. Factorize, and x is 0 or negative 2. Now it says find the coordinates of the points and distinguish between them. Distinguish between them means find whether they minimum, maximum, or neither. Right. So there are y values. Now we're going to substitute into a table. Our 2 values are negative 2 and 0. Even though it's written that way, I must put negative 2 first or I'll confuse myself. Negative 2, 0, before, between, after. Substitute in a value to see. 0 there, we know. There we are. Derivative equal to 0. This time I'm going to use difference of squares. I could have taken the 1 across and got a plus or minus square root. Here's my x values. Substitute into the original to get the y values. I keep saying original because people make the error of substituting into the derivative, and they're always going to get 0 because these came out with putting the derivative equal to 0. Table, values of stationary point, x values, -1 and 1. We're going to test before, between, after. 0 there. So, we've looked at the relationship between f of x and f prime of x. There's f of x. There's the graph of f prime of x. Notice that when f prime of x is below the axis, below the x-axis, the blue part, then it means it's negative. Whether a function, a graph is positive or negative, it depends on whether it's above or below the x-axis. It's positive there, negative there, positive there. Now have a look at the gradient of the original function, positive until there, which is where the graph, the derivative cuts the axis. Now the derivative's negative and the function has a negative gradient. Isn't that wonderful? Positive here, so the function has a positive gradient. So there's the relationship. Now we're going to compare f of x with f double prime of x, the second derivative. We differentiate again. Now, here are a whole lot of examples. This is what would be called an investigation. I'm not going to tell you anything at this stage. I'm hoping you'll discover it. We're going to draw the graph of a function and the graph of its second derivative. So I differentiated again. I'm not too interested in the derivative at the moment. So there we are. The red, there's the function. The blue, there's the second derivative. Now, it's a horizontal line above the x-axis. And because it's above the x-axis, it's always positive. So it's greater than 0. Now, being greater than 0, the whole way means that this function corresponds to a greater than 0 second derivative the whole way. I'm going to take that shape and I'm going to classify it under second derivative positive. Negative parabola, like that. If I differentiate again, second derivative is negative, below the x-axis. Second derivative is negative. So I have above 0, now it's below 0. So I'm going to take this shape and I'm going to put it in another column here. So I have two classifications. Second derivative positive, what's the shape of the original? Second derivative negative, what's the shape of the original? Right, let's go on to, this is called a cubic function. We're going to draw them quite soon. There's the second derivative. There's the function. Now, the important thing is whether the second derivative is positive or negative. That's where it cuts the axis. So on that side, it's below the x-axis, negative. On that side, it's above the x-axis, positive. So let's draw a line and let's categorize it. Let's have a look. When the second derivative is negative, we have that purple section of the graph. So we're going to slot that there. When the second derivative is positive, we have that green section of the graph. So second derivative positive, we'll slot that there. On we go. Another graph. Here we are. That's where the second derivative cuts. It's positive before -2, negative after -2. So let's draw the dividing line. Let's categorize it. Right. Purple corresponds to second derivative positive above the x-axis. Let's put that in its place. There we are, positive. Green, second derivative negative. Below the x-axis, second derivative negative. and there's the function. Let's put that under second derivative negative. Fun, hey? Let's go on to one more. It's actually quite interesting investigating maths like this. There's the function, there's the derivative, there's the second derivative. So the second derivative itself is a parabola. It cuts the axis, so it's above the axis, until then below the axis, and then above the axis. So the second derivative is negative when less than 0, between 0 and 3, positive less than when x is less than 0. It's negative when x is between 0 and 3, and then it's positive after x equal to 3. Let's divide those lines. Let's draw up our nice colors. In this case here, second derivative positive, second derivative positive. Let's put this under there. This case here, second derivative is negative from there to there, and there's the shape of the original. Let's put that under second derivative negative. Here the second derivative is positive again above the axis, so therefore there's our shape, and let's put that under positive second derivative. So now we have a whole lot of things to look at. Let's put them like that. Notice all I've done is I've taken these and I've transferred them to compare them here, the shapes. Now all of these have something in common. All of these have something in common. See if you can see what. I'm going to give you a hint. It's something to do with the shape. I can drink out of these, but I can't drink out of these. These all are hollow upwards. These, the hollow is downwards. So that's called concave. They're known as concave up. So these all, the hollow is up, the cave is up. Cave highlighted up. There's the cave. And those are all hollow down. So concave down. There, that way. So all you've got to think is a cave facing downwards. Oh, the hollow is above. And that's what we call concavity. So we can use that to find the nature of second derivatives. If we have a look at this one here, we've done it already using the table, but let's do it using concavity. First derivative, 2x minus 8 equal to 0 at x equals 4. Therefore, second derivative is 2. Now that's positive and concave up. The cave is facing upwards, like this. We can drink water from it. Concave up. The way to remember it is, if you have a look, this is a parabola. You know a parabola is shaped that way. So positive x squared means if you differentiate twice, you get a constant for your second derivative, and it'll be positive, like a smiley parabola, smiley for positive. So therefore, positive second derivative is always smiley. Minimum. Let's look at this one. This one had 2 stationary points. So there's our second derivative, 6x minus 6. I've differentiated the derivative. Now I'm going to investigate what happens at minus 1, what happens at 3. Now if you have a look, you can see straight away, if I put minus 1 into there, I'm going to get a negative. I'm not even worried too much about what the number is. I really am not. And because it's negative, think of the parabola with a negative x squared. It's unhappy. Concave down at x equals 1. When I try 3 in there, I can see I'm going to get a positive. I don't bother to work it out. Equals positive, so it means concave up. Positive means you have a smile. Negative means you have a scowl. There we are. Local maximum, of course. Local minimum. Right, here's an exercise for you to do. Try them yourself, pause, and then have a look at the result. It says find the coordinates of the stationary points on the equations. Well, derivative equal to 0, solve for x. That gives you the x value stationary point. Substitute back into the original to get the y values, and you have your stationary points. Distinguish between them. Well, differentiate the derivative to get a second derivative. Substitute each x value into that second derivative to see whether you're going to get a positive or negative. You don't need to actually find the value, just as long as you can see whether the second derivative is going to be positive, smiley, or negative, unhappy. Right, the first one. Differentiate equal to 0. I can divide through by negative 2. Differentiate. Factorize. We have two x values. Thank heavens for calculators. If you don't know how to use the memory banks, ask your teacher or friend to show you, somebody who does know, because it's so much easier to put negative 1/3 in the memory bank, and then you just put recall, 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 and you don't have to keep typing in negative 1/3 every time in your calculation. And that'll give you 35/27, or 1 5/27. Substitute the 2 in, and we get 14. We now have the stationary points. That x value with that y value, that x value with that y value. Now we find the second derivative, because remember, we don't know whether that is a local minimum or maximum. So we're going to see whether for this point the second derivative is positive for a smiley or negative for a scowl. So there it is there. Now at negative 1/3, if you substitute a negative into there, this is going to be positive. And I can see straight away the whole thing is going to be positive. Greater than 0 at negative 1/3. Smiley, happy, positive. Local minimum at negative 1/3, 35/27. If I take 2 and put it into there, I can see straight away, well, that's negative 24. Yes, that's going to be negative at 2. Negative, unhappy, scowl, therefore local maximum. Differentiate, equal to 0, factorize x values, sub in the original, and we have our stationary points. Second derivative. We differentiate the derivative. Now we say negative 1/3 in there. Oh, I can see that's going to give a negative. 1 in there, I can see that's going to give a positive. So at negative 1/3, it's negative, unhappy, scowl, local maximum. At 1, it's positive, happy, smile, local minimum. Differentiate, equal to 0, factorize x values. Oh, I love this negative 1/3, don't I? Promise you next question there's no negative 1/3. Substitute in the two values to get the y value. If you know how to use the memory bank on the calculator, you'll love doing these. Second derivative, so I differentiate the derivative. 6x plus 4 at negative 1/3. Well, that's negative 2 plus 4. It's going to be positive. At negative 1, negative 6. Oh, it's going to be negative. So positive at negative 1/3. Positive. Positive people smile, happy, minimum. Negative at negative 1. Negative people unhappy, local maximum. We can't differentiate that as it stands unless you're a math buff who's done advanced calculus. So we multiply it out. Differentiate, equal to 0. Solve. There we are. I promised you wouldn't get a negative 1/3. It's now 2/3. Substitute. original that is. Substitute an original. There we are. Now we need to know whether it's local maximum or minima, so we're going to find second derivative, differentiate the derivative, 6x minus 14. At 2/3, 2/3 times that small number minus 14, definitely negative. Unhappy, maximum. Positive, take 4, put it in there, 24 minus, yeah, definitely positive. Positive, smiling, positive person, local minimum at that point. Differentiate. These are getting so easy. Equal to 0. Divide through by 3. Factorize. X equal. Oh, this is a problem here. We've got two x values the same. It's almost like the stationary points have come together. Well, let's find the y value. Only one substitution. That's great. Second derivative. So I differentiate the derivative. Substitute the 1 into it. And I get 0. Now, I haven't had that case. I know about positive second derivative. Happy, smiley. Negative second derivative. Unhappy, scowl. This here is what we say is inconclusive. It doesn't tell us enough. At our stage of maths, it's likely to mean point of inflection, but you know, once you're studying it and you're going to be a maths professor, there are all sorts of graphs which don't have points of inflection, which actually have zero second derivative. So we're going to have to draw up the table. We've got to go back to the old method. So you've still got to know the old method. Now notice, second derivative didn't work, so we throw it out. We're not going to use it. We're going to use derivative now. At 1, we know is 0. Test before 1, such as 0 itself, we substitute. There's the derivative. Substitute in there. 0 there will give us a positive. And after 1, such as 2, we'll get a positive. Oh, there we are. There's the shape. Up, there, up again. So there's your point of inflection. At 1, 0. Now let's have a look a bit further. Looking at that curve alongside, it can be divided into two sections. Have a look. I hope you can see the two sections. Concave down, concave up. There are two sections. And there's the dividing line. There's the point of inflection, the point of transition. Now notice concave down means second derivative negative. Concave up means second derivative positive. And second derivative is 0. It's occurring between negative and positive, which means there's only one number that occurs between negative and positive, and that's 0. So means second derivative is 0. Now notice it's not a stationary point, this one. So you can have a point of inflection which is not a stationary point. That's why we're doing this here. We had a point of inflection just now, which was a stationary point, but now this one's not. But you can see the definite change in direction. This one says, no, I'm diving. Oh, hang on, I'm going to come out of it. Like a plane diving. A plane dives, and then it's got to come out or it smacks the ground. So at some stage that plane has a point of inflection. So find the point of inflection on the curve of that. Now this is pretty straightforward. Notice second derivative 0. So I'm going to take that, differentiate. What's going to happen now? Differentiate again. Now that's equal to 0. Solve for x. Point of inflection, we need the y. Substitute back into the original. There we are, into that one. Memory bank would be so useful. Gives us that answer, and there's your point of inflection. The second one. Differentiate. Again, for second derivative, equal to 0. Solve for x is equal to 1. Substitute into the original, and we get 2. There's your point of inflection. Pretty straightforward. Usually in an exam this is only worth one mark, but it's a mark you can get then. Exercise, just find the 2 points of inflection there. Pause, try it yourself. Differentiate. Again for second, equal to 0. Solve for x. Now we know the x value. You've got to find the coordinates of the point, so we take -1, put it into the original. There's the y value, and there's the point of inflection. Number 2, derivative. Differentiate again, second derivative, equal to 0. Solve for x. Back into the original. Oh, memory bank, please. There's your y value. There's your point of inflection.